um, discussion. So thank you, Evan, for agreeing to lead this discussion. All right, go on.
Okay. Yeah. Okay. Good. Yes. Okay. So, yeah, I'm Evan. I'm from Basel, and for those of you who came during the weekend, I gave a talk on Friday already, where I talked about magnon-mediated superconductivity in essentially this kind of structure here, where we had one upper TMD, one lower TMD, and an antiferromagnet in between. And then, as motivation, I kind of showed some different setups where the interface plays an important role. And the idea for this discussion session was kind of just to go a little bit more into details about some ideas, some aspects of these examples, which I just mentioned briefly on Friday. Now I have also considered magnon-mediated superconductivity in these kinds of systems in several papers over the past few years. And I kind of want to branch out a little bit, start looking into other effects also than magnon-mediated superconductivity. So I'm hoping kind of we can have some nice discussion which will give both me and you some ideas about interesting directions we can go in to exploit essentially the interfaces. So what I will do is I will start to repeat kind of some of the things I said on Friday about magnon-mediated superconductivity, and from there I will go kind of into this first example here. Then I will jump to interface-induced spin-orbit coupling, and I will sneak in a couple of works which I didn't talk about on Friday. And then finally I will go here. But, we'll see what we have time for, and hopefully there will be a lot of discussion. Okay, so on Friday I showed you this. I had two TMDs. I had an antiferromagnetic insulator in between. And assuming they are lattice matched like this, essentially the upper TMD couples more strongly to one of the sublattice of the antiferromagnet, and this shifts the Fermi surfaces in a way which is favorable for interlayer pairing. And I showed that I could get some exotic kind of interlayer pairing between electrons in the two layers, which it turned out was even topological. So here the color is the phase, and the height here is essentially the magnitude of the gap. And to show this, we used some model like this. Okay, so I'm a theorist, right? This constitutes the perfect model for me. Here I have some hopping Hamiltonian. I have some Heisenberg type Hamiltonian with some easy axis anisotropy along the z direction. And I have this coupling term. And then based on this, I introduced some Holstein-Primakov transformation, and I could write down essentially an effective interaction between electrons in the two layers. So now I have an A electron here, spin up, spin down, spin down, spin up. And this magnon carries a spin up, or spin 1 up, okay, and mediates the effective interaction between the electrons. Okay, so the issue in these systems is always what is the critical temperature. And this depends very sensitively on this parameter J bar, which is the coupling strength between the localized spins in the antiferromagnetic insulator and essentially the electron spins. And just to take the naive estimate, we know that from BCS theory, the TC is essentially the characteristic magnon frequency times e to the minus 1 over lambda. This is the effective electron magnon coupling strength. And it's given by essentially the electronic density of states on the Fermi surface times the interaction strength. And the interaction strength follows from here. Here we have an interaction vertex. This is J bar. There's another one here, J bar. So this vertex here describes essentially interaction between electrons and magnons, right? And then here, this is a magnon propagator. And then you know that magnon propagators are proportional to 1 over omega m, 1 over magnon frequency. So here we get essentially df J bar squared divided by omega m. This is like the naive estimate. So this lambda here needs to be reasonably big to have large critical temperatures. Otherwise, the critical temperature will just be completely suppressed. So how can this now happen? So in most electronic system, the density of states, this thing here, is roughly proportional to 1 over the electronic energy scale, right? So 1 over some hopping, if you wish. This T is typically the largest energy scale. So essentially, for this one to be large, we need this J bar to be big. And in particular, bigger than the effective magnon coupling strength. So the question is now, how do we do this? This is question 1. Can we kind of ensure that this J bar is large? Question 2. Can we somehow manipulate our material? Can we do something to it? Can we do something to our stacks so that we increase this J bar? Anything else? Let's start there. Do any of you have any experience or any thoughts about kind of how to go to this regime? Yes, in the back. Yeah.
Just to get a little bit more of intuition towards the how you're modeling the TMT being coupled to the AFM layer. So what is the coupling between AFM spins and TMT electrons? Is this ferromagnetic exchange or anti-ferromagnetic exchange?
This doesn't actually matter so much to us. You can take it to be both ferromagnetic and anti-ferromagnetic.
Okay, so the sign of J does not play.
Doesn't matter so much. I mean, so we have. I mean, you have one TMD here, right? And this one has an up band and a down band, and the spectrum looks essentially like this. So you have the K point and you have the K prime point. Let's see. This is what we call A up and A down. And if you switch the ferromagnetic to antiferromagnetic coupling, it means that essentially the effective Zeeman that you feel because of coupling to the antiferromagnetic insulator, it just switches, right? So instead of shifting like this, you shift like this.
Thank you.
Yeah. Oh, yeah.
So just to ask a silly question to make sure I'm pointed in the right direction, J bar is the exchange coupling layer to layer, correct?
Yes, exactly.
Yeah.
So it's this one here. So you have some, in here you have electronic energy scale, right? This is this T essentially. Yeah. You have this J bar, which is this coupling, and then you have some J1, which gives you the magnon spectrum inside here.
So to first order, I would imagine that depends on the nature of the materials and the extent to which the wave function pokes out of plane.
Yes.
So as a selection criteria.
Yeah.
If one doesn't have that, just to throw out an option, putting a single layer of graphene in between, because I know those pi star orbitals stick out pretty far.
Yeah.
That might form an effective exchange bridge between your antiferromagnet and your TMD. Just, I'm not familiar with all of those material systems and what the electron wave functions look like.
So you're saying essentially put some graphene in between here.
Yeah, because then you'll have the pi star orbitals poke out pretty far above and below the atomic layer. And
Something like this.
Yeah. And that effectively provides a linker that could overlap with the electron density.
So even if you put
both
something
ways.
in between, it essentially enhances the exchange. Yeah.
Unless your materials are already doing that, in which case you're just
Okay, then
adding
it doesn't
problem.
help. Yeah. But so this is known then. That kind of. Do you have some?
What part of it? That shape of the
pi orbitals of graphene
that
gas.
shape of the pi orbitals is well known, and exchange being wave function hybridization is well known. I don't know if anybody's done that
Yeah.
exact measurement in graphene.
Pi orbitals. So for graphene, right, you have some sort of sigma orbitals way down here, and it's these Dirac cone orbitals. They're made of pi orbitals, right? So basically, you occupy some of the pi orbitals.
So sorry. So now I'm having a nomenclature train wreck in my head.
I'm just confused, and I think
I was under the impression that conduction electrons and graphene
are in those orbitals.
are in the orbitals
They're
above
pi.
and below the plane. Correct. Yeah. Okay. Thank you. I may have transposed pi and pi star,
I'm not a graphene person.
but yeah. So it's a 2-deg floating above and below the atomic layer.
Okay. Great. I think a very interesting suggestion. We haven't really considered this before, so something to look into. Great, thanks. So one other thing which we considered was you apply kind of pressure, just hydrostatic pressure essentially from on top here and maybe from the bottom. And I mean, naively, this should increase this exchange, right? What actually these colors here correspond to are, you assume that there is some strain. And if you have some strain, you will essentially change the coupling strengths within the antiferromagnet. And this could modify essentially how soft your magnon dispersion is. And of course, if we make the magnon dispersion softer, this could make the effective coupling strength larger. So it would kind of have to, make the effective unit cell bigger, right? I'm not so familiar with these strain experiments or how you apply it. Yeah, of course.
Sorry, I would have naively imagined what I was thinking that you were going to say is that if I just apply overall pressure, so unidirectional.
Yeah, from above and top.
Yeah, yeah. If I just press it, then I guess I just push the layers closer together.
Yeah.
And the overlaps are bigger.
Yes.
Is that the right way of thinking?
That's my naive guess, at least, for how you can do it, yeah.
Okay, thank you.
Okay. Great. Any more comments? If not, then I will move on a little bit. So I also told you that essentially one way to make this proposal of ours was to have this lattice matching, right, that we have here. And in the end, we came up with two proposals. One was kind of based on lattice matching, as in this case, where the point was that the electronic orbitals, which are important when we have weak hole doping, are the ones living close to these M atoms here. And then, if you have lattice matching, basically these M atoms are closer to one sublattice of the antiferromagnet. And because of this, you couple more strongly between these two than between this one and this one. Now, the other option was you had some sort of layered antiferromagnet, where essentially you have the RTMD, and then you have the up spins here, and the down spins here. And just because of this, the lower one couples more strongly to the down sublattice than the up sublattice. Now, the material that actually made us think about this one first, before we got to this one here, was chromium triiodide, 3-iodide here, which I think got kind of popular, especially with this paper here. So chromium iodide has this essential lattice structure here. It's some van der Waals magnet, and the chromium atoms have some magnetic moment. Now, if you have a lot of these layers, it's known essentially that this is a ferromagnet. If, however, you only have a few layers, there was some experiment where they did magneto-optical, they looked at the magneto-optical Kerr effect, so you have some Kerr angle here. The Kerr angle essentially measures the magnetization of the layer. And if they had a single layer, they found this hysteresis curve here, which essentially indicates that there is some magnetization. If they had 2 layers, on the other hand, now essentially they found that there was no magnetization up until a certain critical magnetic field where you had some jump. And the way they interpreted this was that essentially you have 2 layers now with magnetizations in opposite directions so that the net magnetic moment is 0. And then at sufficiently strong magnetic field, you just polarize it completely and you get a large magnetization. Okay, and this is the 3-layer case. In the 3-layer case, there will still be some more upspin than downspin. Okay, and now we are thinking if we have something like this 2-layer, this could kind of fit nicely in between for our proposal. Okay, then the question is, of course, how big is this J bar? And this was measured in this paper here. So again, they had this material and they put some TMD on top of it, tungsten diselenide in this case. And here they had a lot of layers, so this was a ferromagnet. Okay, and then they looked at the photoluminescence intensity here. And they did so at 1 temperature, which is above the critical temperature of magnetic ordering in this chromium iodide, and 1 below the critical temperature. And the red and the black, the blue curves here now corresponds essentially to the spin bands of the TMD. And what you see that is that above the critical temperature for magnetic ordering, they coincide. When you go below the temperature here, essentially this peak shifts a little bit. This shift corresponds to 3.5 millielectron volts. So this is a kind of small shift. And it is not big enough to give us a significant coupling. So this is kind of the reason that we didn't really consider chromium iodide for our proposal. And instead we needed to look for some other material. But the problem was for other materials which had this layered antiferromagnetic structure that we wanted, it was actually kind of hard to find some experimental values for what the spin splitting is. What is this J bar? So my next question for you is kind of, how do you measure J bar? How do you extract it? We also looked into some DFT calculations, but the problem is that the DFT calculations, they usually varied quite a lot, and there didn't seem to be sort of consistent results on what J bar is. So do you have some sort of input on, yes, how can you extract J bar experimentally? Yes.
Very naive suggestion, which is, what about thinking about what about measuring exchange bias?
Exchange bias, yes. So by this you mean applying a magnetic field.
So I field cool the antiferromagnet in some orientation, and then it's exchange bias some ferromagnetic layer, and then I should expect to see a shift of the loop, and the amount of the loop shift is related to J bar, I think, in a straightforward way.
Yes. Okay. Yeah. Good. I think so. This is kind of related to also, I don't remember exactly if they did this also in this paper. I don't think they presented the okay. No, I think there are actually results like this in this paper, now that I think again. So I think they've done this here, and this is basically where they got this 3.5 millieV from, in addition to kind of this curve here. Yeah. Tungsten diselenide, yeah.
Yeah, this is, but you need the chromium triiodide bilayer and a ferromagnet interface layer, not a TMD layer. So you need, and then you need to measure the magnetization of that TMD layer, for instance, by MOC or some other way. So maybe they did that and used a different van der Waals magnet. I don't know. But this structure itself, you can't measure exchange bias because
Here you can measure it, yeah.
you cannot.
You cannot, okay.
Yeah, you need an antiferromagnet interfaced with a ferromagnet,
Yeah, you need...
or
okay,
a ferrimagnet, but
I
you
see,
need
yeah,
something that has that you can see the magnetic moment switching.
Okay, so the problem here is this one is not a ferromagnet.
Correct.
That's what they're saying, yeah.
Yes.
Okay. An exchange bias. Okay, but so what do you mean by exchange bias actually? Is it...
What do I mean by it?
So it's you say it has to be a ferromagnet, but couldn't I say that kind of there's a shift in the bands here?
No,
That's not, you wouldn't consider that to be exchange bias?
it's
effect?
not exchange bias.
Oh, okay. Yeah.
Is that shift proportional to exchange? Maybe it's related, but the point is that exchange bias would be deadly simple.
Yeah. Deadly simple. Okay. So I would say this J bar is sort of also some kind of exchange, right?
Yeah. So I guess maybe my point is that the measurement that I suggested wouldn't be exactly what you want because it isn't the same two materials.
Yeah.
But if you could make the tungsten diselenide a ferromagnet,
Yeah.
then it would be.
Okay. Yeah.
I don't know how you make it a ferromagnet, but that's
We probably
you're a
don't want-
theorist, so you can figure that out.
So I can do it.
Computer, you
Yeah.
can, yeah.
Okay, yeah. Thanks. Okay, so this again goes in kind of the direction of seeing how, seeing how the exchange or the coupling that we have on this interface affects the electronic structure here. I guess this applies both to exchange bias, if that was possible, and kind of this results here. But are there also other ways to do it? Yeah.
So I'm just not want to make sure I understand the data shown there.
Mhm.
So that's a spontaneous polarization
Yes.
that appears in the presence of the chromium triiodide.
Yes.
So can't you just take that temperature dependence to extract an energy scale?
Yes. You can. Yeah. So
doesn't maybe I'm just missing something. Doesn't
Yes.
that give you the parameter that you want?
yes. So for this stack, it does. Certainly, it does. And our problem is, so for this stack, we know what the value is, kind of. But I'm interested in other stacks as well, right? And for these stacks,
So ones that are not optically active?
maybe not. So at least, when looking through the literature, it was very hard to find values for these other kinds of stacks. For instance, when we had this MBT, let's take that as an example.
So which layer do you want to replace?
So let's say I have some MBT and I put some TMD next to it, tungsten diselenide or something like
Yeah,
this.
then the same measurement should work.
The same should
So
work, yeah.
basically you get it, at least the way I would think about this from like in a magnetic semiconductor perspective,
Yeah.
is you get an effective field
Yeah.
due to the exchange. And then you assume you have a two-level system in your exciton, and you look at the polarization as a function of temperature,
I see, yeah.
and that'll be a Brillouin function that will then give you the effective field that the spins are feeling.
Yeah.
And then through some theory, some model, you can then relate that electric field to an exchange coupling.
Okay.
So,
yeah.
but I think that should generically work for when the TMD layer has optical transitions that are reasonably well understood.
Yeah. I see. Okay. Yeah. So this seems like really this is the way to go then. Okay. Thanks a lot. Yes. So let's maybe, yeah.
What is the desirable order of magnitude of the exchange coupling that your proposal
This
requires?
one here?
Yes.
20 to 40 maybe.
MeV.
MEV.
Right.
Small, small M.
So have you considered this super exchange where the interaction is mediated by other atoms?
You mean similar to the graphene proposal that we had before?
I think so. Yeah.
Yeah. No, well, no, not until it was proposed here. Okay. So, just to go back to the starting point, the motivation of kind of this work that we had was you had some magnetic material, you put it next to some TMD, and the magnetic material and the magnons in there can give you some sort of superconductivity or some, you change the properties of this TMD in a way which I think is very interesting. So just a bit more generally, if we want to think away from superconductivity, what kind of interaction effects due to interfaces are you interested in? Can be very wide, right? Exchange bias, I see. That's your kind of... Yeah. Mm-hmm. And what? DMI, yeah. Okay. So more like the left one here, yeah. So exchange bias. Okay, so what's interesting about exchange bias? Everything. I see, yeah.
Okay, maybe Greg, you should briefly tell the more physical aspect of exchange bias.
All right, so exchange bias. One of the things that interests me about exchange bias is that it's useful, but another thing is that it's poorly understood.
Yeah.
The kind of definitive paper was like Ivan Schuler and somebody I'm blanking on their name, like from 1999.
Okay, yeah.
Like the most recent like definitive review. And so, but exchange bias is simple as you expect. I have an antiferromagnetic material at the interface. With the ferromagnetic material at the interface, there's exchange. The antiferromagnet is very insensitive to magnetic field. It doesn't really care if I apply a magnetic field because it's compensated by many layers of alternating spins.
Yeah.
And but yet it still exerts exchange at the interface with the ferromagnet. So then there's a bunch of phenomenology associated with that. For instance, there is a shift of the hysteresis loop of the ferromagnet due to this exchange. There are other things, including enhancements to the overall anisotropy. So both unidirectional and uniaxial anisotropy changes.
Yeah.
And there's some even more exotic phenomena. But in 3D systems, which 99% of the work is done for, there is some confusion because exchange bias works equally well, and I'm going to forget the antiferromagnetic terminology, like G-type and A-type and all those, but where the, if I, for instance, think about the TMD case that you have, or sorry, the van der Waals case you have, you have a bunch of spins at, all the same in one interface, and then the other direction, so it's planes of spins.
Yes.
But you can have antiferromagnets in 3D systems where you cut it along different planes, so it could be alternating in the plane, and you still get exchange bias.
Yeah.
And that is attributed to a statistical polarization of exchange at the interface. And also, it's expected that defects play a role, and it's very confusing.
I see, okay.
But exchanging magnetic films is super, super important in spintronics. So for instance, if I want things to work at zero field, how do I apply a field artificially? And the easiest technological answer is I add an exchange bias.
Okay, yeah. I see. And also, Thanks. It's interesting, okay.
Can you actually vary the, because I know, about exchange bias and all this, but you cannot really control this, vary it, right? This trend, like with a knob, like with an external magnetic field, can you?
I don't, okay. I mean, you can control the antiferromagnetic domains by field cooling, and so you can kind of depolarize the antiferromagnet and get different values of exchange bias, and people have done a lot of work on that, so they can tune the value. In most applications, they just want it to be as big as it can.
Yeah.
So that's interface engineering, and basically a growth problem for 3D materials.
Mm-hmm.
In van der Waals materials, I don't know that there has been a very extensive study of exchange bias. And I think there are opportunities there because you don't have as much disorder in these materials in terms of like, you know, in 3D materials, I always have roughness. So if, let's say I take the simplest 3D antiferromagnet that everybody knows about, nickel oxide.
Yeah.
So I grow nickel oxide 111, it should be planes of spins, right? But it's never planes of spins because I never have perfectly atomically flat nickel oxide, and even if I did, let's say that if there's any substrate, like if I grew it perfectly epitaxially, any angle of the substrate polish means that I have terraces,
Yeah.
right? Which is, all of this is just very, very hard to control. So there's always roughness, and yet exchange bias works robustly, and that's confusing.
Okay, yeah. This is nice. Okay, thank you. Very interesting. I have a lot to look into, I think. Now, okay, let me move on to talk about spin orbit coupling. So the basic case was the one that was shown here. And the idea is essentially if you put some magnet close to some material with large spin orbit coupling, then you will see some DMI on this interface. And we saw, for instance, some talk on topological magnons. Typically DMI, that's how you get topological magnons in some system. Okay, so I just wanted to show you some recent work of ours, which was published, I think, a month ago, something like this. So what we do is essentially we propose some way to make a vortex, a magnetic vortex, which is the configuration that we see here. And the idea is you have some magnetic material in blue, and you have some sort of circular shape, and then you have a material with large spin orbit coupling on the interface here around it. And then similar to this case here, this should generate some DMI on the edges here. And the DMI vector is now always out of the plane along the set direction here, because it's always sort of in the interface, in the interface plane. So you can model this now as this term here. You have some DMI vector, and then it's n cross the derivative of n, where n is now the Neal vector. And then you can take this standard term here, which essentially tells you that the Neal vector should, not be spatially varying. And now, based on essentially the competition between, or the you have some sort of skirmion, depending on, with some length scale, which depends on this j and k. And if you have this DMI term, essentially you can truncate the skirmion when you're halfway, and then you get this vortex configuration. And then we made some sort of ansatz for what this skirmion looks like. So here I have now theta and phi. Those are define in which direction the spins are pointing. And then you have this var phi here. This is now the angle which tells you where are you, basically. So this now describes a vortex with winding number n. And essentially the energy of this system is now jn squared minus d to the n. And this means that if d is sufficiently big, it should be energetically favorable to put some vortex into the system, just from the DMI that we have on the interface here. And vortices are typically generated in this kind of system when you have a ferromagnetic system. What we do in this work is essentially come up with some proposal where you can do it also with antiferromagnets. And the reason that this is typically done for ferromagnets is that the stabilization of these vortices typically rely on the dipolar interaction. And there is no dipolar interaction for antiferromagnets. Okay, and because antiferromagnets have fast dynamics, this means that essentially you can make these vortices much faster and also much smaller than you typically can for ferromagnetic systems, and this is kind of the advantage of this approach. And we had some talk before lunch about encoding quantum information inside. In that case, it was essentially the helicity of a skyrmion, and you can imagine similar kind of ideas also here. Okay, so this was just the ansatz. Then we also did some micromagnetic simulations, which I will now show you. So just watch this one. So this now has some DMI, and you show there is some relaxation. There is some skyrmion somewhere here now, which is slowly moving, some vortex, which is slowly moving towards the center. So it's essentially attracted to the center. And okay, we can do this kind of relaxation process for several different D strengths. And you see that if D has some value, you just get no vortices in the system. You increase it a little bit, you get vortices, or you can even get 2 vortices if you make D even stronger. Okay, so the question is now a little bit, how easy is it to realize this kind of system experimentally? And maybe you have some input on this. So, I mean, again, this is some sort of theorist view, right? I just make this system, the DMI should point like this, I assume this is the model, and then, I get vortices, nice. But do we have that kind of control over the spin-orbit coupling at interfaces, kind of? Yeah.
So there's a couple things that are a significant challenge here. The first question is about length scale. I mean, is that to scale your diagram in terms of roughly the number of lattice constants you want for this vortex?
No, it's not to scale.
Oh, so how big?
It should be, let's see. Fairly small, I think. Yeah, I will have to look up the number.
Yeah, so
sure. Yeah.
If you're in the ballpark of 10 nanometers?
So basically it's the size of it. I mean, it's essentially the same size as typical skyrmions. So if you have some kind of material which holds skyrmions, then it should be roughly the same size.
Craig, do you know what that size is, roughly?
Depends on exchange.
It depends on the material. So yeah, skyrmion size is like a competition between DMI, anisotropy,
yes.
MS, like it is a very, so you can easily do multiple micron size skyrmions, or you can do, I was part of a DARPA program where the challenge was 10 nanometers and below. And what we found was that basically that's at the edge of the distribution. Like we succeeded because we found one that was really, really small and we said, look, there it is. But actually the average is more like 25.
Yeah.
So that's possible, hard. I think the biggest problem is if you need that interface to be vertical.
Yeah.
I don't immediately have any ideas for how to build that. If you can make a ring of DMI material and put a cylinder on top of it, that I think you have a chance of doing. But then the materials interface is in the plane rather than out of the plane, and I don't know how that might affect the direction of the DMI you introduce here.
Yeah.
Are you saying like essentially applying a vertical electric field or something to break a symmetry?
I'm just thinking, how would I build something like this? And I'm saying I can imagine building a ring of platinum and then putting a disk of magnetic material on top of it. I can't imagine like putting a wedding ring of platinum around a disk of magnetic material at these length scales. I don't know how one would do that. Well, I guess, so if you wanted to try a real hero experiment, you could maybe try making a core shell nanoparticle and then mill off the top and bottom with a fib, maybe. So you're left with a disk around the equator.
Mm-hmm. Yeah.
You could try that. Greg just volunteered to try that.
Okay, thank you. So I just wanted to show you as well. So then we also looked into some oscillations. So essentially, if you put a current through your now conducting magnet, you can essentially drive some oscillations of the vortex position here, which are now close to the terahertz regime. So this shows you essentially, now we introduce some set, which is essentially just the position. And then just because we're theorists, we made some complex coordinates out of it. And you can have this kind of star-shaped motion. So the vortex is now roughly here. And then I'll start this motion, and you see the vortex kind of going back and forth around this direction. And then you see it slowly kind of turning around. So now it's more like this. And so on. Okay. And you can also split it off with a magnetic field. So essentially there's now two kinds of modes. There's one rotating like this, the one rotating like this. And if you apply a magnetic field, they will split off. Okay. I also kind of, I see. Okay. Unfortunately, there are not so many dragons in Brazil, as far as I know. So, okay. I can't really say that this has anything to do with Brazil, unlike Bill's nice talk, but the reason I put a dragon up here is that I gave a poster presentation on this work some time ago. And then one very, very senior professor in the field, very well respected, comes up to my poster and he sees this word, chiral spin liquid. And he goes, "So, have you heard the story about the boy and the chiral spin liquid?" And then he just, without waiting for me to respond, he just goes on to say, "So, there's this small boy walks up to Santa Claus. And Santa Claus asks, 'So, what do you want for Christmas?' And the boy says, 'I want a live dragon.' And then Santa Claus says, 'Nah, that might be a little bit difficult. So don't you have some other wish?' And the boy goes, 'I want a chiral spin liquid.' And then Santa Claus says, 'So, which color should the dragon have?' Okay, I was a bit shocked, I have to say, to experience this, but it was kind of nice as well, because it, in some sense, highlights what the point of this work is. So we make some reasonably simple model for essentially some spin system like this. Each ball represents a spin. And we have some exchange-like interactions within each chain here. And you have some DMI within each chain, and also some magnetic field. And then you have some Heisenberg-type coupling in between here. And using this fairly simple model, we are able to show that by choosing essentially some modulation in the DMI strength here and in the magnetic fields with some periodicity of 4, this model can host some chiral spin liquids. And realizing chiral spin liquids are very, very hard. Also, if you have a chiral spin liquid, it's very difficult to demonstrate that you have a chiral spin liquid, because essentially it has non-local order, it has non-local entanglement, and probing this is very difficult. So kind of the selling point of this paper is that we come up with a reasonably simple model which may host it, and hopefully, yeah, I can't maybe give you a dragon, but maybe I can give you a chiral spin liquid. Okay, but this is very difficult to make. And the main proposal that we had was these synthetic quantum systems like ultra-cold atoms and things like this. I think in some paper which we were building on, they also proposed that you take some magnetic material And then you take some strips of essentially some material with strong spin orbit coupling. And doing this, you can make spatially modulated DMI, which is one of the key ingredients that we need for this material. So since we had primarily these ultra cold atoms in mind, I haven't looked so much into the details of whether people can make this or not, but in case you kind of have some experience on this, I would be very interested. Okay, just to give you some more details, the approach that we use is something called coupled wires. It dates back to this paper here from 2002, where they looked into essentially the fractional quantum Hall effect. So if you have wires, right? Now imagine it's not spin chains, but instead it's just electronic wires. Then you have some out-of-plane magnetic field. You can take the vector potential to look like this. Essentially, it increases as you move in the y direction, and the vector field is always pointing in the x direction. And then essentially what this amounts to is you have a dispersion relation here for chain 1. For chain 2, you shift it, because this one is now 1 bigger, and you shift k, this is now kx basically. You shift in the kx direction, and then you have 3, 4, 5, 6. And if you are now at a certain filling, essentially you will open gaps, and this leaves you with some edge modes. And the way they did this was essentially using bosonization. Using bosonization, you can capture interactions in one dimension, more or less exactly. So essentially, you look at the effective excitations that you have next to the Fermi points of this one-dimensional system. And then you introduce the interaction and the hopping between chains perturbatively. And these now, in the bosonized language, take this form. So here I now describe the degrees of freedom that I have close to my Fermi point in terms of some bosonic fields theta and phi. This is now plus for the right-moving fields and minus for the left-moving fields. And in the absence of any coupling between the chains, I get this Luttinger liquid Hamiltonian. When I introduce the interaction between chains, I get some interaction term like this, which is some cosine times some field here, which is now some linear combination of my thetas and my phis. And now, depending on what this relation between phi, this big phi, and these thetas and phis are, I can get the different fractional quantum Hall states. So the reason that it's nice to have it in this form is that this Hamiltonian, essentially these two terms, can be understood in terms of the renormalization group, and it corresponds, in fact, to essentially the Kosterlitz-Thouless phase transition, which has this flow. So essentially, if you start out here, the interaction close to 0, which means your system is described by this term. If you start out in this green region here, you flow to strong coupling, which means that this term dominates your physics. And that's when you get your fractional quantum Hall. And you can kind of see easily here that you couple one node L. This is now some index which describes you which chain you are talking about, to some L plus 1. So you couple this one with this one, this one with this one, this one with this one, but these two are not coupled to anything, therefore you have chiral edge modes. Okay, then what we did in this paper was essentially we apply this to the spin chains. There's two important quantities. There's the magnetization, which is controlled by the magnetic field. And there's the dispersion shift. So basically what we do is you have your spin chain, you map spins to fermions through the Jordan-Wigner transformation. And then the DMI gives you essentially a shift of this cosine dispersion relation, which here is this kind of sawtooth profile. Okay, and now you introduce the interaction between the different chains, and it takes this form. And if you choose your magnetization and your dispersion shifts in a certain way, then a particular interaction, for instance, the one looking like this one, will be what we call resonant, which means essentially that there is no e to the ikx, some fastly oscillating prefactor in front. And then essentially this term is the only important interaction term in the system, and we get some analog of the fractional quantum Hall effect, which is also some chiral spin liquid. Okay, and then we also derive some phase diagram for this, which now is in terms of k. This is some parameter, the Luttinger parameter, which describes how strong are the interactions within each chain, and this V perp, which tells you how strong are the interactions between different chains. And you can write down different interaction terms, and this can give you kind of the phase diagram for different phases. Okay, just some very quick intro to this paper, but it's a long paper with a lot of details. So yeah, you should discuss with me or go to this paper if you want to know all the details. One more remark at the end. So if this is the most important interaction term in my Hamiltonian, the basic excitations that I can make here is I sit in some minimum and then I jump from this minimum to a neighboring minimum. This is the basic excitation. And within this approach, you can fairly easily calculate that the spin associated with this excitation is 1 over 2n, where n is now some integer. Can be 1, 2, 3, and so on. And we know that if you flip a spin half, that's a spin 1 excitation, whereas here you get now spin half, spin quarter, and so on. So these are essentially fractional spin excitations, which is one of the properties that you typically want for chiral spin liquids. Okay. Moving on. We had a lot of discussions already on magnon-photon coupling. This paper is from a couple of years ago, and yeah, I read it. I found it kind of interesting, and it falls nicely into what we have been trying to discuss here. So I thought I could bring it up, and then maybe it's a good idea, maybe, yeah, there are some problems with it. I'm not so sure. So the idea is you have some cavity, and you have some ferromagnet. And now you want to couple the magnons of this ferromagnet to the photons within the cavity. And one way to do this is you say that the magnons in the ferromagnet couple to the magnetic field of the cavity, and this gives you some sort of coupling of this form here, where you have some coupling strength Gm. But what they propose in this paper is instead you make an interface between the ferromagnet and a topological insulator. Now the topological insulator has some electrons, and it's described by this Hamiltonian here. So you have essentially sigma times the momentum, but then you also have an electromagnetic field, so it should be momentum minus the vector field. And then you couple the edge modes on the topological insulator to the ferromagnet, so we have also this term here in the Hamiltonian describing the electronic system. Okay, so now, again, a theory is drawing diagrams. Basically, you can integrate out the electrons. The electrons in the topological insulator can mediate some coupling between the magnons and the photons. So it's essentially just like this. I have, let's say, some magnons here. The magnons interact with the electrons in the Ti via this vertex. And the electrons in the Ti, they interact with the photons via this vertex. And okay, in the end, you generate an effective coupling between magnons and photons. And the coupling strength for this that they give in this paper is given by this expression here. So you see it's proportional to J, for instance, which is the coupling between magnet and the electronic spin. It's proportional to 1 over Vf. Okay. And if you take the ratio of this electronic coupling through the Ti and the standard coupling through the magnetic field, you get this ratio here. And they now insert some estimates for J and also Vf into this paper, and they say that this ratio is roughly 15. So essentially they're saying that you can enhance the coupling between the magnons and the cavity photons by putting a Ti next to the ferromagnetic insulator. Yes, question?
Do they comment on the coherence and relaxation effects induced by the conducting edge states?
So, of course, the conducting edge states, they are the ones who mediate the coupling in the first place. But you are thinking about some particular effects, maybe on the magnet.
Well, like, there's like no. Is there a bias? Do you have like how? Do you have a bias on the topological insulator? And a directional like current flow?
There is, yeah. So
okay, so I'm thinking like if you have, let's say, scattering centers.
Yeah.
Since this is like a 2D topological insulator, 2D like surface states and not the helical ones, there's going to be a lot of scattering there.
Yeah.
The scattering is going to generate noise. Just kind of like Johnson-Nyquist noise, right? That's going to be proportional to conductivity.
Okay, yeah.
And this is going to induce relaxation and dephasing. So I was just wondering whether the authors also considered this.
This noise? No, they don't, as far as I know.
Got it. And the other quick question that I had regards the momentum that you have on the Hamiltonian for the... Yeah, so I don't understand that cross Z hat.
The cross Z hat. It's basically...
just Px and Py? That's it?
Yeah. So it's basically... okay, so I think it doesn't really matter so much, right? You can consider either sigma.k, or you can essentially change the basis of the electronic spins. And this corresponds essentially to interchanging sigma x and sigma y. And this is what this cross C means. So I don't think it really matters that much. That's my impression anyway. So, as my question, I mean, I'm not an expert in this. I just read the paper. So I'm kind of wondering if this is something well known, or if this is some completely novel approach, or...
So I'm... Are the excitations just particle hole excitations of the electron system? Because you usually need to couple via excitations, like what you drew on the board.
Yeah.
So
the diagram, you mean?
Yeah. So these exist all the way down to zero energy, and I guess you need the excitations. I don't know. So so is the density of these excitations goes to zero at zero energy? Is that okay?
It's gapped.
Or it's gapped? Oh, the magnetization gaps it. Yeah. Sorry. Okay. Then okay, it's going to couple at a particular energy that's set by J. And then did they have to fine tune things to make sure that the cavity frequency matched some condition with J in order to get it to work? Because otherwise, if these things are off resonant, they're not going to couple very strongly.
I don't think I remember anything like this. No.
Because the coupling looks proportional to J.
Yeah.
It's not inversely proportional to J, but J sets a gap for the electronic excitations.
Yes.
Okay. I don't know. I was just trying to think through it, and I didn't quite see where that was coming from.
I see, yeah.
Okay. So if J is the gap, what is the meaning of EG?
EG, okay, yeah, sorry. This is, EG is basically just the Magnon frequency. And they multiplied it by some H bar, and that's what they call EG.
Gotcha. magnum frequency at 0?
Sorry, not magnum frequency, photon frequency.
Okay.
What?
No, it's okay. I understood now. I was thinking, yeah, it's an interesting idea. I can't understand it right away. There are too many elements.
I see. Yeah. Okay. Yeah. Okay. Yeah.
So that's the coupling that's anyways large, right? So these are microwave cavity to photons. So
yeah,
why is it that? So what's the point?
So I think the point that they're trying to make is, okay, so the coupling is proportional to square root of n, right? So you need essentially a big magnet, and somehow if you make the system bigger, there's more decoherence.
It's to proportion, in principle, it's proportional to density. You
Yeah,
just
okay,
need to
yeah.
do good so mode matching. So
Yes.
if you do good mode matching, then you can have a small magnet.
Yeah. Density. Okay, so it's yeah. It's
No, it's proportional. So if you have a perfect mode matching,
Yeah.
is the spin density. The issue with cavity systems is that you have the magnet is smaller than the cavity size. So you want to increase the size of the magnet to match the cavity volume size.
Okay, I think we agree, but I think that the invariant quantity is n. So you're kind of saying, if I mode match, then I make the magnet just as big as the cavity, and then I can adjust the density, but I'm adjusting it to get n. If I, and of course the mode isn't uniform in the cavity, so if I concentrate the mode, I get stronger coupling. So I still think that n is the right, I mean, it's not a big deal. I'm just, yeah, the insistence that it's density. I think if I can make very high density stuff, but if I don't have enough of it, then.
Yeah, but that's the mode matching issue. So that what I'm, yeah.
Yeah, okay, so
we're
we're going
same.
around and around. But
yeah, so
okay.
I'm saying, so if you have high enough density,
yeah, got it.
It's just, yeah.
We agree, yeah.
okay. So if you couple to, if you have a ferromagnet, right? Then you can couple to essentially the photons through the magnetic moment. Now there's also this paper here, which is on archive for a few months, where they consider something similar for an antiferromagnet. So here, as we talked about briefly again, they consider some uncompensated interface, where essentially you couple more strongly to one of the sublattices of the antiferromagnetic insulator. Then you again have the same kind of coupling between electrons and the gauge field here. And then I mentioned that when you do a Bogoliubov transformation in my talk, essentially if you can be in the situation where this UQ is big and this VQ is big, and this you can have because you're doing Bogoliubov transformation, and then the condition is that U squared minus V squared is 1. So essentially this means that you couple to a large spin on one of the sublattices, and this effectively increases your interaction. Now the second is, of course, and probably the most important one, is since you are coupling the magnons in the AFM to the photons through essentially through the electrons, you can have some coupling between an AFM, an antiferromagnetic magnons, and the photons. And then in this paper they also calculate some sort of mode hybridization between the cavity modes and the magnon modes due to this. So again, coupling antiferromagnetic magnons to photons. Is this something that is well known? Or is this also no?
We discussed this a little bit last week, but
Yeah.
Greg, I would love to hear your opinion.
Experimentally, there is not a lot of work, but there's been several papers, theory papers.
Proposals, yeah.
Yeah, proposals. I mean, you have to have some way to break the symmetry, right?
Yeah.
And that's, like, this is a way.
Coupling to one sublattice, yeah.
Yeah.
Yes.
Axo also commented on like some experiments he has coupling photons to the outer magnet.
Yeah.
Magnons, not the antiferromagnetic ones. But well, then we're not gonna discuss semantics, but yeah.
So actually, I will be talking about at least the theory side about that tomorrow. But maybe so there are. I'm not. So here you're talking about resonant coupling. Yes. So this is. So I would say that there is. Okay. You can think in terms of terahertz cavities that could couple resonantly directly to the magnons via dipolar fields, right?
Antiferromagnetic magnets,
yes. Then you can think, so if you are outside of the resonant regime, there is of course a lot of work in Raman scattering, right? So where you have two photon, two magnon, two photon process. So scattering of one photon would generate in two magnons. And then I believe also in the field, and these are kind of, experiments from already quite a long time ago. And I think also in the field of ultra-fast dynamics, the people use or are trying to just couple in different ways to these magnons. So, pump probe experiments, but that's not the resonant regime, right? And I think there is also, besides what Axel showed a couple of days ago, is also paper from Isabella Boventer and I think Matthias Klaui and Martin Weides, where they show also another system in which they have resonant coupling to an antiferromagnet in a cavity with this kind of, but without but also the antiferromagnet with low frequency. And there is an older paper, so in the 2017, where there is a group in Oxford where they also couple some resonance, so planar resonator to some, I think it's I don't know, some material where they see some antiferromagnetic fluctuations, and this is the first paper that I know in which they show some kind of resonant coupling. But I would say that in the terahertz regime, there are recent papers where they show this kind of coupling without the topological insulator, but with a terahertz cavity.
Okay. Great. Well, thanks a lot. Then at least I look a lot forward to your talk tomorrow, where I can hopefully learn a lot more about this. And this was kind of what I had planned to discuss with you. So if there's nothing else, then thank you.
So thank you, Greg. I'm looking at you and I almost said Greg. Thank you, Evan, for the nice discussion. And it surprised me so much, discussion on the topic. At the beginning, I thought, well, it's going to die very quickly. But no, you really held on to it. Wonderful. So I guess it's a good time to break away. We have a coffee break, and then we come back for Greg's talk.